Math 1314, Chapter 6, Matrices and Determinants, Section 1, Matrix Solutions to Linear Systems, Video 5, Matrix Goal Number 2, Reduced Row Echelon Form, Gauss-Jordan Elimination. In the previous video, we learned how to, what is it we learned how to do? We learned how to use something called Gaussian elimination with back substitution to turn a system into an augmented matrix, turn the augmented matrix into row echelon form, turn that back into a system which was ready to solve using back substitution. The convenient thing was the very last entry, very last row, I should say, was ready to tell us what one of the three variables was equal to. And then back substitution into the modified version of the system allowed us to find the remaining values of the variables. However, it's possible to push the matrix even further to do less work at the end. Because think about the process that we did. We took a system, turned it to a matrix, fiddled with the matrix, turned it back into a system. The bottom equation was ready to give us a solution, and the back substitution gave us the other solutions. But what if we could take a system, turn it into a matrix, fiddle with it, so at the very end, it contained our solutions and eliminated the need to back substitute? Well, such a thing is possible, and it's using something called reduced row echelon form, and the process is called Gauss-Jordan elimination. Recall that reduced row echelon form is a continuation of row echelon form. Recall that row echelon form has two criteria. Number one, the first non-zero entry in each row is 1, and we call these things pivots. So when you're looking across the row, the first number you see that isn't 0 is 1. And the entries below the pivots, don't know why we have an S there. The entries below the pivots are 0. So every time we had a 1 as the first non-zero number in a row, everything below it was a 0. Reduced row echelon form, I'll learn to type one of these days. Reduced row echelon form has one additional criterion, and that criterion is the entries above the pivots are 0. That should say pivots. So in other words, when we create this 1 as the first number in the row that isn't 0, in addition to zeroing out everything below it, we also zero out everything above it and get as many zeros above and below these ones as we possibly can. Now, to achieve reduced row echelon form, henceforth known as RREF. So later in this video and in future videos, I will refer to reduced row echelon form as RREF. To achieve reduced row echelon form, modify Gaussian elimination as follows. Each time you get a pivot, a 1 in the first non-zero entry in a column, in a row. Should have proofread this before I started the video, but it's okay, I'm human. Each time you get a pivot, a 1 in the first non-zero entry in a row, use row combinations to eliminate all other entries in that column. Specifically, use that 1 and multiples of it to eliminate everything above and below it. This enhanced process is called Gauss-Jordan elimination. The advantage is no back substitution is required, as the final matrix should contain the solution in the augmented column. Assuming a unique solution exists, this will be explained in the last video. For now, a unique solution will exist. So let's jump right into it. We're going to solve the system using Gauss-Jordan elimination. Now, you may recognize this as the same system from the previous video, so we should get the same solution. But I wanted to use this one to show you how we could push this beyond row echelon form into reduced row echelon form, and also how you can multitask a little bit, because this can get drawn out. Every time you do a row operation, you rewrite a new matrix. So you're going to look for spots where you want to try to work a little bit more efficiently. All right, so I'll show you where some of those spots are. All right, let's start by turning this into an augmented matrix whose first row is 3, 1, 2, 31, whose second row is 1, 1, 2, 19, and whose third row is 1, 3, 2, 25. Sometimes it helps to put the numbers and then draw everything around it to make sure the brackets and the augmentation bar are the right size. All right, so your first focal point is getting a 1 in the first position in the first row. So we need a 1 here. And remember, you can get that by either doing a scaling move or a swap. If you did a scaling move, it would have to be 1/3 R1, but that would create fractions in the top row. And don't get me wrong, it would work. But if you have the option of bringing fractions into a problem or not bringing fractions into a problem, I think I know which one we would do. Let's just do a row swap. Now this time I'm going to do a row swap with the third row. In the previous video, I did a row swap with the second row because it didn't matter, but I do want to point out that it really doesn't matter. Besides, if there's a 1 elsewhere, you may not have a choice. So let's do a row swap with the first and the third rows. And that will make the next matrix. We'll draw the bracket last. The third row becomes the first row, so 1, 3, 2, 25. The second row stays the same, 1, 1, 2, 19. And the first row becomes the third row, so 3, 1, 2, 31. All right. And at this point, we've got our first pivot in place. Remember, a pivot is just the leading one, the first one in a row, the first non-zero entry being 1. All right, so we got our first pivot. Now here's where we can streamline the process a little bit. When you create a pivot, when you create a 1 in the first non-zero entry in a row, you're going to use it to eliminate every other number in that column. So I'm going to use the 1 to eliminate the 1 below it, but I'm also going to use that 1 to eliminate the 3 below it. Now, you can do combination moves simultaneously as long as you're not adding into the same row more than once. So in this case, I'm adding into the second row and into the third row, and neither one of those are my multiplier. In other words, I can use the first row to simultaneously change the second and the third rows. So how would I set those row operations up? Well, in order to use this 1 to eliminate that 1, I need the pivot, the one highlighted in yellow, to become a -1. So our first row operation is going to be -1 times the first row, and we're going to add it into the second row. But at the same time, I can ask myself, how can I use this 1 to eliminate this 3? Well, if the 1 were a -3, that would work. So we're going to multiply -3 times the first row and add it into the third row. And notice that I'm writing the row operations in the row that's going to change. Now, you can do these mentally, or you can write them all out like we did before. I am going to try to talk them out. We're not changing the first row. We're just going to use it. Now, the good news is I already know what's going to happen in the first column. Should give me zeros, but let's play it out. Let's start with this row operation. We're going to multiply the top row by -1 and add it to the second row. This is going to go kind of fast. 1 times -1 is -1. Added to 1 is 0. Remember, I'm multiplying by -1 and adding. -1 times 3 is -3. -3 plus 1 is -2. Multiplying by -1. -1 times 2 is -2. -2 plus 2 is 0. And we're doing it here also. -1 times 25 is -25. -25 plus 19 is -6. Okay, let's do the -3. Let's do the next row operation. -3 times the first row added to the third row. All right, multiplying by -3, then adding to the third row. -3 times 1 is -3, plus 3 is 0. -3 times 3 is -9, plus 1 is -8. -3 times 2 is -6, plus 2 is -4. Over here also. -3 times 25 is -75. -75 plus 31. Let's see, opposite subtract. Looks like it's going to be -44. Make sure that's correct. Looks good. All right. So by doing the two combinations simultaneously, we've saved writing an extra step. You just got to make sure that you set up the moves correctly, which means determining both of these row operations and then very carefully playing them out one at a time. All right, let's see where we are in terms of reduced row echelon form. We need a 1 in the first pivot, which we got. We need zeros elsewhere in the column, which we also have. Good. Our next move is to go to the next row and turn the first non-zero entry into 1. So we need to turn this into the number 1. Well, that's pretty easy. You can turn any number into a 1 by multiplying by its reciprocal. So our move is going to be to multiply the second row by -1/2. And let's see what matrix this gives us. Let's see, our first row stays the same, 1, 3, 2, 25. Our third row stays the same, 0, -8, -4, -44. But our second row, we're multiplying by -1/2. 0 times -1/2 is 0. -2 times -1/2 is 1. 0 times -1/2 is 0. And -6 times -1/2 is 3. All right, so far so good. We now have our 1 in the first and second pivot positions, and we've got the zeros in the rest of the first column, but now we need to create zeros in the rest of the second column. In other words, now we need to use this 1 that we just created to zero out the 3 above it, but we also need it to zero out the -8 below it. So let's think about what those row operations would be. To get rid of the 3, I need to turn the 1 into a -3. So we're going to do -3 times the second row and add it to the first row. Let's go ahead and figure out our other row operation. To use the 1 to eliminate the -8, we need to turn the 1 into an 8. So we're going to do 8 times the second row, and add it to the third row. All right, let's see what this gives us. Our second row is going to stay the same. And really the first column is going to stay the same, because if you think about it, I'm using this 0 to change the numbers above and below it, but 0 won't change it at all. And if I set up my row operations correctly, this 1 here is going to zero out what's above it and what's below it. So we might as well go ahead and write our 0 here and our 0 here. So really we just got to focus on the third and fourth columns. All right, let's do the first row operation. -3 times the second row added to the first row. Well, that's going to be easy here. -3 times 0 is 0, plus 2 is 2. And here, -3 times 3 is -9. -9 plus 25 is 16. And now let's do the other row operation, 8R2 plus R3. All right, going back to the 0 here. 8 times 0 is 0, plus -4 is -4. 3 times 8 is 24. 24 -44 is -20. Let's see where we are. We have our first pivot. That's supposed to be highlighted. And we have the zeros in the rest of the column. We have our second pivot and the zeros in the rest of its column. Now we have to get our third pivot and use it to zero out the numbers in the rest of that column. Now, luckily, the number above it is already 0, so I see 2 more row operations in our future. We need to do a scaling move to turn the -4 into 1, and then a row combination to get rid of the 2 above it. Let's move this matrix over to the next page, and then we'll continue. Okay, so here's the matrix on the previous page, and we are currently trying to turn the -4 into a -20. Excuse me. We're trying to turn the -4 into a -1. That will be pretty easy. We can turn any number into a 1. I think I just said -1. We're trying to turn the -4 into a 1. And to turn any number that's not 0 into 1, you multiply by its reciprocal. So we need to multiply by -1/4 across the entire third row. That will not change the first row. That will not change the second row. But we will multiply the third row by -1/4 to get 0, 0, 1. -20 times -1/4 is 5. And now everything is just about in place. At this point, we technically have row echelon form because we have 1s as the first non-zero entry in each row and zeros below it, and we're almost to reduced row echelon form. because in order to get that, we need the third column to contain zeros everywhere except where the 1 is. And we already have a 0 in the third column, second row. So the only other place we need to achieve a 0 is where that 2 is. So what row operation can make that happen? How can we use this 1 to get rid of that 2? Well, we would need to turn that 1 into a -2. So we're going to do -2 times the third row, add it to the first row. And that will get us in reduced row echelon form. All right. Our second and third rows are not going to change. We're not even messing with the second row, and the third row is just being used as a multiplier to fix the first row. And now we need to pull off the rest of the moves. Well, let's think about it for a second. When we use the third row to change the first row, nothing's going to happen in the first two columns because of those zeros there. You can play it out if you want to. In the first column, -2 times 0 is 0, plus 1 is still 1. So nothing's really going to change there. And in the second column, -2 times 0 is 0, plus 0 is still 0. You'll notice that these perfect columns don't change as we move forward. So you can just look to the right. All right, so now we need to perform this row operation over here, but it was designed to turn the 2 into a 0. -2, let me circle it as it goes. 1 second here. All right. -2 times 1 is -2, plus 2 is 0. We're expecting that to happen, but we have to do it on the augmented column as well. -2 times 5 is -10. -10 plus 16 is 6. And at this point, we've achieved row reduced echelon form, reduced row echelon form, meaning the first non-zero entry in each row is 1. And every row that contains one of those pivots, every column that contains one of those pivots is 0 everywhere else in the column. Now, at this point, we could turn it back into a system of equations, but think about what it would say. The top row would say 1x is equal to 6, because there's no y's or z's. The second row would say 1y is equal to 3, because there's no x's or z's. And the third row would say z is equal to 5, because there's no x's or y's. Our last column contains our solution. So reduced row echelon form is convenient in the sense that there is no need to finish solving a system of equations. It is already solved inside the matrix. Is it a long journey there? Well, that's a matter of opinion. With practice, going from system to augmented matrix to reduced row echelon form is very consistent. In fact, this is how computers are programmed to solve systems of equations, because if you think about it, there's very few decisions that have to be made. You pick this number, scale it or swap it to turn it into a 1. And if you'll notice the multipliers, every time we did a row operation, a combination, our multipliers were just the opposite of the numbers we were getting rid of. 1 and 3, -1 and -3. Over here, let's change colors. We were getting rid of 3 and -8, and our multipliers were -3 and 8. And the reason they're opposite makes perfect sense. The number that we're multiplying by is 1, but we need to turn it into the opposite of the number we're getting rid of. Same thing happened over here. This was a 2, our multiplier was a -2. So you can boil this down to just saying, let me change this number as the multiplier on the 1, add this row to that row to create the 0, and at the end, you get your solution. With some practice, it becomes real straightforward.